Yeah, first of all, thanks for having me. I know this is a video recording, so it's not the same as actually talking to most of you live. But on the other hand, I am glad that I can share threads and ideas, especially in this time from far away. My name is Manu Prakash. I'm a faculty at Stanford, and much of what we do focuses on very broadly what we call frugal science, the idea of making science broadly accessible to people. And that includes everybody, not just scientists, but trying to build technologies that could scale at a global scale. And we've been doing this for the last 10 years. And there are examples of this work, including things that some of you might have used, like Foldscope, some of our diagnostic tools like Octopi, some of our environmental tools like the Plankton Scope. I think today what I'll do is I'll give you a 10-minute, 15-minute premiere of just what we've been doing in the context of COVID. And then time permitting, I can just share one or two things about other projects. I know this is a hackathon for all of you. And I think I chose to talk about some of the COVID projects with all of you to ensure that there is a lot that you can do still, although you are not in your physical workspaces, for example. Much of the work that I'm about to describe was done in a distributed manner around the world, but with the focus of deploying solutions. So I'll start with this picture that you can all see. This was a cartoon that showed up in a French newspaper maybe a month or so ago. This is one of my postdocs in my lab fighting the COVID virus. And you can see that snorkel mask, which I'll briefly talk about. I think, there are very few positive images of COVID, and much of that comes from healthcare workers really putting themselves on the front line, physically putting their bodies on the front line. And I think we have to be truly thankful to much of the healthcare infrastructure around the world for where we are. And although the world overall is not in a good situation from a context of COVID, there is, so I think much of the work you'll hear today is driven by us talking to clinicians around the world and learning from them. Everything that I'm describing is open access, so any of you could jump in and engage in the project that I'm about to describe. They're all described also on our lab's website, so if you go to the bottom of that link, you can find that. And then if any of you want to reach out to me, my contacts are on this link. So let's kind of begin. The summary of what I'll talk about is I'll briefly discuss 5 or 6 projects in the lab that we have launched in the context of COVID that are starting to scale. I'll start with PPE and solutions for PPE, transition to talking about ventilators. I'm sure all of you have heard about ventilators. Then I'll talk a little bit about how to build tools to essentially fight misinformation and provide the right kind of information around contamination and decontamination of masks. And then I'll transition a little bit to talk about diagnostics and what we are doing wrong in diagnostics. Why have we not been able to put a stop to this virus? And then finally, in the very end, I'll talk about an idea about distributed manufacturing, which is associated with what is broken in supply chains around the world, and how do we, post-COVID, how do we look at the lessons that we have learned from this and try to rethink of a world where supply chains are far more resilient, especially when it comes to critical care. So here is kind of the buffet, and I'm going to go rapidly through several of these examples. So firstly, I don't work alone. The work I'm describing is from my lab, including fantastic students in the lab who literally dropped everything that they were doing, including their thesis work, their PhD defenses, and jumped on and engaged in these projects. So I'm actually quite grateful to many of the individuals. But then also, we have engaged clinicians and industrial partners all across. Some of them are listed up on the top. And it's fascinating as an academic lab working in a university. COVID has taught us that when the time is right, you can really build massive scale operations. For example, for some of the projects I'll talk about in the PPE world, are collaborations with clinicians from 20 countries around the world, all working together towards a solution. So, the silver lining to all of this is that it is indeed possible to operate at a global scale and deploy solutions rapidly, all the way from design to validation and manufacturing and deployment. And I think the key piece here is validation. And then, of course, another piece is deployment. Validation is important because in a crisis mode, you can come up with all kinds of ideas, but if you don't validate them, you're adding noise to the problem. Lots of good enough ideas are not good enough from an implementation perspective. So you really have to dive deep and ensure safety of many of these ideas. And so, as many of you are working, if you're thinking about enabling and coming up with solutions in the medical space, it's extremely important to be thinking about safety, which I'll mention. But much of this work is also described in preprints and papers that we have shared. So here are a bunch of websites that you can find much of this work on, but let me just walk through from the beginning. And I think the heroes of the story are also individuals that we have had the chance to engage. So something that you're all doing in this hackathon, it started as a puzzle to me when I started seeing early March these big challenges and incredible talent, but it was distributed. So, one of the roles that I've played for many of our projects, and what I believe is almost essential, has been to be able to bring a singular question and a singular way of working to make sure that many communities can actually come together. And I'll talk about these communities and how we were able to build communities around specific projects. If you're trying to fight a virus like COVID all by yourself, that's not sufficient. You have to generate good ideas, but very quickly build momentum and build people that will actually support your idea. So the other aspect of this is, if some of you are working on COVID, the big advice from the last 3 years of our work is talk to clinicians. It makes no sense for you to build something, get there, spend hundreds and hundreds of hours, and in the end realize that, oh, I never spoke to a clinician, and hence that solution actually does not work. So a big factor for all of the work that you're about to see is deep engagement with clinicians. Okay, so let's start with something that you've all heard about, ventilators. So, the challenge is pretty clear. All of you know what mechanical ventilators are by now. Burkina Faso, for example, has a total of 11 ventilators. Last I checked, around in April. Sierra Leone has 13. And, Bangladesh, for example, for a country of, if you think about 170 million people, the number of ventilator per person would land up around one ventilator for 340,000 people. And as the pandemic, although it has in under control in many places, lots of places it's not under control, especially in the global south. And that brings to this notion of, how do you really provide this life critical support to people? And the community's response, and especially the engineering community's response, has been very quickly ramping up on building lots and lots of open source designs. I'm sure all of you have read about tons of these open source design. Most of these ended up being around an early response of automated ambu bags, which is this classic. It was essentially firstly a hack that these ambu bags that are used to be squeezed to support a patient in an emergency for a few minutes to an hour, which essentially provides some kind of volume control associated with how much air you will pump into a lung. The problem is, the lung is a very delicate object. So if you're designing something that is going to pump air into a lung of a patient, it has to be, you have to provide all levels of controls to a clinician to really be able to support a patient for between 2 to 3 weeks, which would be the actual duration of time a person would be on a ventilator. So although literally hundreds of designs and possibly thousands of teams around the world ramped up on building these automated ambubags, none of them have been actually used on patients because it's not safe to put a patient on something like this over a long period of time. So that leads to this challenge of how do you rapidly innovate but also not give up the features that a clinician needs. So we started thinking about this problem early on, and the goal was to build a classic full feature ventilator, which is what is used currently in an ICU, but something that will be rapidly manufacturable, and secondly will be completely open source so anybody in the world could actually build it. And the framework is that although you can build it, you still have to go through the local regulatory process to make sure that what you have manufactured actually meets the regulatory requirements. So we built a team around this. This is a team effort between Stanford, University of Utah, and Brown University, with lots of industrial partners that I'll talk about. And this is what the ventilator looks like. I don't know how technical I need to get to, but one of the things for you to think about a ventilator, on the left, what you see is a schematic, is what we call pufferfish. So pufferfish is a full feature ICU ventilator that's completely open source. So I'm not aware of another example of a ventilator that provides these sets of features and is openly accessible. And our goal primarily was to build around the medical supply chain design. So one of the challenges has been in COVID context, there has been supply chains have been blocked because they're already spoken for. So in some sense, you can think we don't have a shortage of ventilators. We have a shortage of parts that go into a ventilator. So we were able to design ventilators from parts from completely other industries, which we could still verify. And one of the nice things about something like this, I'll just show you, this is the earlier prototype. And what you're looking at is the ventilator operates on pressurized air. Either we generate that through a turbine, a compressor, or you have medical air. And this is Hong Chuan in the lab who's been leading the project, building it all. So this is a time lapse. I'm just gonna skim through this quickly. He's putting together the pneumatic circuit. So to the very left is the pneumatic circuit. Now this is just a prototype assembly. These are the control valves. There's all the electronics. This actually operates on a Raspberry Pi, something that many of you actually use. There's a screen. And in the end, this is a test prototype of what we call pufferfish. But now you get to watch it breathing. And this is a video of a clinician actually testing this in a hospital. And I'll let this play. So just as a background, the pufferfish is at the back, that white box that you see. What you're seeing here in the front is what is called a test lung. So this is a equivalent of what a patient lung would look like, and it's inflating and deflating because air is being passed into this lung. But now what Brian is going to do, a fantastic clinician at UCSF, he's going to induce a cough. And what this reminds you that you might be designing solutions as engineers, and until we had spoken to Brian, it had not occurred to us that a patient that's ventilating can cough, and it happens many times. And suddenly all the pressures that you are reading and measuring go haywire. And you have to immediately adapt to it to ensure that you can actually handle a situation like this. So, what ends up happening is when you're building solutions, you have to remember what the real life challenges are for that device. So I'll just let this play because it's kind of a fun video. You see he's banging on this.
You notice that it only dumps back to that pressure. You can't control that initial cough from nothing. You're not gonna be, that's almost like they don't even need to know. Oh, they're getting ready to cough, so let's get ready to lower the pressure. So that was a cough.
Yeah.
And your pressure maintained. That's exactly what you want to see.
Mm-hmm. So that's kind of a moment where you can build and design whatever you want, and then a clinician comes in and they provide just beautiful insight that allows you to improve the tools. So where Pufferfish is currently, it's a global consortium. We have manufacturing partners in Chile, Kenya, India, Nepal. The consortium is starting to grow, and we are trying to essentially ramp up to get an EUA approval in the US, and primarily also get EUA approvals in Africa and India. And one thing that we're very proud of from with our manufacturing partners is this would be the first time a full feature ventilator will actually be manufactured in India and Africa. And this is the perspective of looking back on the context of COVID, is what can we do in response to this crisis to actually build enough infrastructure to bring these tools and technologies to people around the world. So these are the teams in India that is part of our core team. There is a team in Nepal, there's a team in Kenya, and this group is starting to grow. And one thing that's valuable about openly sharing your ideas is communities pick them up and build. And literally the Nepal team built the entire ventilator, I think, in less than 5 days from the moment we shipped them the kit of parts. And of course, there's still a lot more work to be done, but this global and distributed manufacturing of critical components is actually feasible. So this is ramping up. I'm going to switch to the next project. And this is unfortunate. You're watching a recorded talk, so I can't take questions, but you guys can send me questions later. I'm going to switch gears a little bit, which is the challenge of how do we protect our healthcare workers. So this is something that you've all seen the toll. And one of the challenges has been is the shortage of personal protective equipment, PPE. When we started looking at this in March, we had a realization that we could use recreational equipment, which is these full face snorkeling masks. I don't know how many of you love the ocean and go snorkeling. These are full face masks that are used underwater for snorkeling. They're widely available, they're recreational equipment, and their history lies in gas masks. But on the other hand, the traditional PPEs that you use are very difficult to fit on a face and usually leak, while the elastomeric seals happen all across the face. So we started asking ourselves, how could we take a supply chain and very quickly invent a tool that allows us to provide personal protection? So what you're seeing in here, I don't know if you can see my cursor. Give me a second. Okay, I can't bring my mouse here. Okay, I'll just have to talk through it. What you're looking at is the mask itself, and then you're looking at a little coupler piece and a filter. We rapidly prototyped this piece. We partnered with our manufacturing partners. We submitted this to regulatory bodies. We got a regulatory approval in Europe. And in the end, in a short period of a month, we were able to deploy around 40,000 of these around the world. And we're still deploying these in Haiti, in Nepal. We're starting to ramp up things in other places. And so I think one of the things that was about the solution was the fact that we were able to get it in hands of clinicians. And although it kind of looks silly when you think about a clinician wearing a snorkeling mask, but it provides a type of a protection that protects both the breathing, because there is a viral filter, but also protects the eye. So it's a combination of a filter and a face mask. These are the kinds of pictures that give us joy when we see patients and doctors around the world intubating patients, dentists, anesthesiologists across the world. I think currently these are being used in all the way around 20 to 22 countries around the world. And that happened fairly rapidly once we opened up and shared our files. This is just some data on distribution. So I'll switch to talk about diagnostics briefly. And let me skip this video first. Let me just share this video. I'm sure all of you, I don't know how many of you have gotten a COVID test so far, and how many of you are still waiting to get a COVID test. Currently in the US, the situation is quite dire, in which the delays can be as long as 1 to 2 weeks. And since you know the peak of a COVID patient already just lies around 2 weeks, if it takes so long, the duration of time that a person is spreading the virus, you didn't stop them. So then it's almost useless if 2 weeks later you find out and then you decide to stay home. That doesn't actually stop the virus. So what we need is we need to rapidly detect who has COVID and to do it at a cost that's feasible. So I was on a call with NGO in Bolivia, for example, and they mentioned that not only does it take such a long time, it can take as much as between $100 to $200 per test for the RT-PCR tests that are done. I mean, I don't know how you all think about it, but that's just absolutely outrageous to think about accessibility. So of course, this leads to certain sets of populations that will not get any test, while other sets of populations can get a test. And then of course, the delay is a huge issue. So we started thinking about this and we invented what we call a handifuge lamp, which is a type of a molecular nucleic acid based test that costs $1 and it does not require any electricity. So the first place that we designed this for when we were working on this was for indigenous groups in the Amazon. So unfortunately, COVID has spread to the most remote part of the world. And what that does is it's quite scary because in remote parts of the world, neither do we have ICUs nor do we have diagnostics. So we started thinking about what is the simplest test that you could do. In some sense, this is a type of a test that could literally be done at home. You take a little tube, you spit your saliva in it. There are certain sets of processes and steps that you have to go through. And one of that step is a centrifugation step. So we invented a centrifuge. Some of you might have read about our prior work on what we call paperfuge. So I'll just show you the centrifuge. These are the tubes that the test happens in. You load the tubes. There's a little handle, and I'm sure, I don't know how many of you have used the hand flashlights. And right there, we're using that to essentially spin the sample. The sample gets spun, and eventually when you stop, you process through certain sets of steps and you get a color code, either red or yellow based on whether the sample is positive or negative. So the yellow indicates that it's COVID positive, the red indicates it's not. So this is a test that would take somewhere around half an hour to do. You can do it at home. And again, one of the challenges is how do you deploy these tests in a regulatory framework? So we're still planning on submitting something like this to the FDA. Although we have built the test, we can't roll it out until we have gone through the regulatory process. So, but this is another example of thinking a little bit about when you're designing something, think about the community that you're trying to target. Okay, so I'm gonna end with, or maybe I'll briefly describe N95 masks. And this is related to what I had said about personal protective gear. But one of the challenges there is how do we make millions and millions of N95 masks per day? So I'll repeat that. We need in the US somewhere of the order of 3 million masks per day to protect people. And that in the past has happened through centralized facilities, very large plants that can manufacture a large amount of PPEs, but you cannot make another factory in a day. It would take years to establish and expand the capacity. We started asking ourselves a different question, which is, could we manufacture a critical component in these PPEs, which is this molten, melt-blown fabrics that essentially make a PPE, which is this filter that can filter out aerosol droplets, for example, that are 300 nanometers. And I was thinking about this and it kind of struck, I'm not sure how many of you have tasted cotton candy machine. Do you know what a cotton candy machine is? This is the sweet that you can eat. And if you've ever looked at it under a microscope, you'd realize it's actually small scale fibers of sugar. So we, of course, you can't make a mask out of sugar because that would just melt. But we actually realized a process by using a hacked version. We bought 6 or 7 of these cotton candy machines from Amazon, and we hacked them and rewired them to build an instrument that allows us to take recycled plastic, literally stuff that you can find around the world. It has a melting process, it melts it and it spins it out in a fiber format, which is what you're seeing right here, which is what we then use for filtration mechanism. So one of the fascinating things about this is that this is a process that now allows us to literally manufacture, in this context, the filtration material, and then there is a sets of process that we can use to build masks out of that. So the way we are taking this project is along the direction of what we call a N95 factory in a box. So could we ship to any country in the world a set of parts that will fit in a small room, that will have the capacity to make somewhere between 10,000 to 50,000 masks per day? So it's not 3 million, it's a fairly small number, 50,000, but it's still, when you have hundreds of them, it's actually an order of magnitude larger than what you can do with these larger plants. So this is a project that's ramping up with partnership with several manufacturers. Uh, so in the very end, I'll just mention a word about misinformation. So we have 2 pandemics. We have the COVID pandemic, and of course, I'm sure if any of you are on WhatsApp and other things, I'm sure you are Facebook or no matter what, you read about all kinds of things that scientifically unproven ideas or things that have absolutely no scientific basis, but then people believe in it. And this was a huge challenge when we started thinking about it. And the only way to fight it is to fight it with good information. That's the only way to fight bad information, is that you have to provide more or equivalent amount of good information for people to be able to make judgment calls. So we started thinking about this, and we built this organization called the N95 Decon, which was an organization focused on providing decontamination knowledge. How do you decontaminate when you have a PPE mask that's not accessible? How do you decontaminate it? And then a major product out of that was publications and videos and YouTube videos. And I don't know if many of you watch Minute Physics. There's a massive amount of, so these are publications that are written for doctors on decontamination methods. And if you go to this website, N95 Decon, you will see all kinds of information that's geared towards medical professionals of how to decontaminate their gear. And I think, again, this is one of the key challenge, is that you have to provide, you have to fight misinformation with good information. There is no other alternative. So if many of you are thinking about projects, this is a very scalable project that you can do at home by read scientific papers, identify, talk to people who are practicing scientists, validate an idea, and then once you've validated it, provide it in a format that is digestible to your own community. This is a huge issue currently because general public does not read scientific papers, and scientists that are working on COVID related projects are currently completely inundated with all the things that they have on their plate. So we need communicators that can bridge that gap. And this was one example, but I'm sure many of you can come with phenomenal design ideas to really fight misinformation. I think this would be an army of people that we need, and it would be phenomenal if you contribute. So I'm going to end here on this slightly sobering post about COVID. The way I see COVID is this picture on the left, which is what we have seen so far is the tip of the iceberg. The vaccine is still, by any nominal means, more than a year away. This disease will continue to spread. Lockdowns are going to be difficult. At some point of time, economies will shatter to a point where they will not have a choice to keep closed. And this is something that you have seen all around the world, including what's unfolding in Latin America, what's currently happening in the US for that matter, what happened in Europe early. And so keep in mind that although we might all be tired of COVID, COVID is not tired of us. So you really need to think about this as the tip of the iceberg. And so anything and everything you do, the current sets of steps that you do actually do matter. It doesn't matter whether in Hong Kong you have COVID or not. This is in my lifetime really the biggest global crisis. I think the next one that we have to tackle after this is climate change, but that's for another day. It's extremely important for you to think about this beyond your own community to see what could be done. And I think I want to leave on a positive note. I often say this, that, you know, we are in a crisis mode, but sometimes good things come out of it. And that's the story of the invention of the bicycle. So I don't know how many of you know how bicycles were invented. It started with a volcanic eruption in 1815 with Mount Tambora, which erupted, and it massively had a blackout all across Europe, where the sky was dark for many, many, many months. And horses that were primarily used for human transport before, uh, it led to a famine, and the horses could not be fed. And at that time, Baron Karl von Drais thought of a new way to move as compared to horses. And that was the origin of bicycles. So if we didn't have that volcano, I'm not sure. I mean, how many years would it have taken to jump from horses to bicycles? So similarly, we find ourselves in a crisis. We are grappling for solutions. We are struggling. But this is also the moment to remember that status quo is not good enough. The kind of healthcare we provide people is not good enough. The kind of access we provide to people is not good enough. The war on misinformation and the damage that it causes is going to be something that will remain with us forever. And many solutions that all of you can participate in will have an impact on the world beyond COVID. So I think I want to stop here, but just remember this, that eventually, uh, you should not waste a good crisis. So let me end and say thank you to all of you. Um, I'm sure you all will have certain sets of questions, but again, if you want to learn more about the work that we do in the lab, you can go to this lab website. If you want to learn about past projects that we have done, you can go to foldscope.com or a couple of project websites that are associated on the web. And if you're interested, you can find me on Twitter and email. And I'll stop there. Thank you.